Okay, so some practice questions with solutions and concentrations. So the first couple are dilution questions, and I think rather than trying to use the dilution equation, which C1V1 equals C2V2, is basically saying that the moles before you dilute is equal to the moles after you dilute. And so all that changes in a dilution is that you're adding water, which is increasing the volume. So volume 2 always increases above volume 1. And that makes concentration 2 go down compared to concentration 1. So this is an equation that people sometimes use as a shorthand way to solve dilution questions. It's actually often used backwards in the lab, where we figure out where we want to end up, concentration 2 and volume 2, what solution do we want to make, and then we work backwards to solve for volume 1 of the original solution. How much of the original solution do we actually need to measure out to start with? But on these IB questions, and particularly paper 1 questions, they like to give you dilution questions, and I think actually the simplest way to solve them is to realize that dilution is an inverse relationship. So there's an inverse relationship between what happens to the volume and what happens to the concentration. So a couple of examples to show what that means. A teacher adds 90 cm cubed of water to 10 cm cubed of this 2 molar solution. So what is the new concentration? So the thing to figure out is what has happened to the volume. Well, you started off and volume 1 was 10 cm cubed. And when you're done, you've added 90 to it. And that means your volume now will be 100. So the thing to figure out is how many times bigger is volume 2 than volume 1. On paper 1, they're typically going to give you pretty simple numbers. So this volume has increased by a factor of 10, we could say. It's an increase of a factor of 10. It's 10 times bigger. And that means we've spread out the moles in the original solution 10 times farther apart. And that means they're going to be 10 times less concentrated, 10 times more dilute. So if the original solution is 2 moles per dm cubed, I know, based on that volume change, that when I'm done, the concentration will now be 1/10 of what it was originally. And so I get 0.2 as my new concentration, which is the answer to the question. You can also see if we had used C1V1, C2V2, if the volume goes up times 10, then the concentration has to be divided by 10 in order for those two changes to cancel out and for the two sides of the equation to still equal each other. Let's try it again. In this one, a teacher adds 990 cm cubed of water to 10 cm cubed of a 1 molar solution. So again, what's the change in volume? Well, the change goes from 10 at the beginning, and afterwards it's going to be 1,000 because we've added 990 to it. So we have increased the volume by a factor of 100, which means the concentration needs to be divided by 100. So if we start at 1, we'll end at 0.01 for concentration 2. So to me, that's a much faster, simpler way to think through a dilution question, especially one with kind of simple numbers on paper 1. Okay, now this is something that they can do on paper 1 as well. It could also be paper 2, but probably more likely a paper 1 question where they want you to figure out the resultant concentration when you mix different concentrations together. In this one, you're mixing 2 volumes, 100 of a 0.5 molar solution and 200 of a 0.2 molar solution, and they're both KCl. So kind of different ways to think about it. Ultimately, what you're really trying to find, if you're trying to find the there we go. If you're trying to find the concentration, then you got to figure out that the concentration, what's happening, get out of here. It's a lot of something happening with my program, sorry. So concentration is moles divided by volume. And so really all you have to do is realize that because you're mixing 2 solutions, the total moles is going to be the moles from the first solution plus the moles from the second solution. And then the total volume is going to be volume 1 and volume 2. So when you do that, you'll have the moles total and you'll have the volume total. So the total volume is simple. It's 300 cm cubed, which is 0.3 dm cubed. And on top, to get moles with a solution is C times V, N equals CV. So you've got your C of 0.5 times 0.1 plus your C of 0.2 times 0.2. And I know that with the decimals, the math can get a little bit tricky. We can always use scientific notation if you want, but essentially you're going to end up with 0.05 and 0.04 on top, divided by 0.3. So then we're going to end up with 0.09 divided by 0.3. And now, yeah, we could do scientific notation if that's throwing us off. 9 times 10 to the minus 2, 3 times 10 to the minus 1. And we will end up with 3 times 10 to the minus 1, or 0.3 moles per dm cubed as our resultant concentration. Sorry for the sloppy solution progress. But that should make sense. If you're checking your answer, right, you started with a 0.5 and you started with a 0.2 and you mixed them. So it should be somewhere in between 0.5 and 0.2. And if you get an answer outside that range, then you've probably done something wrong. You can also see that it's closer to the 0.2 than to the 0.5, which is logical because you used twice as much of the 0.2 as you did of the 0.5. Okay. Moving on. A student obtains 0.1 molar solution of calcium nitrate. What is the concentration of nitrate ions? This is a simple ratio question. You should see that there's 2 nitrate ions, so there's 2 NO3 minuses for every 1 formula or formula unit of calcium nitrate. And therefore, if the concentration is 0.1 mole per dm cubed of the calcium nitrate, the concentration will be 0.2 moles per dm cubed of nitrate ions. And that's the answer. You can apply those ratios that we've used before within formulas to concentrations as well. Okay, the last one is a little bit trickier. It's kind of like question 9 again. You're mixing 2 solutions, and in this one, it just wants to know about the concentration of sodium ions. And so it's kind of a double whammy in the sense that first you're going to figure out the moles of solution 1 and the moles of solution 2, just like we did in question 9, and ultimately you're going to divide it by the total volume, so the 2 volumes combined. But the trick here is that they want sodium ions, and the second solution, the sodium phosphate, Na3PO4, you have to pay attention to a ratio of sodium ions within that compound in and of itself. So that's where the extra trick comes along here. So if we try this one, from the first one, we should get 0.2 moles per dm cubed times 0.2 dm cubed, giving us 0.04 moles of NaCl, which also means 0.04 moles of Na plus, because there's only one Na in each sodium chloride. In the next one, I've got 0.1 is my concentration times 0.2 is my volume, and then here's the trick. So instead of getting 0.02 moles, though, that's how many moles there are of sodium phosphate. There's 3 sodiums in each of those. So you actually have to multiply this number by 3. It's a ratio step. And so the moles here is 0.06. So I've got 0.04 moles from the first solution, 0.06 from the second. That's 0.1 moles of sodium ions total. And then I divide that by the total volume. The total volume was 400, or 0.4 dm cubed. And I can see basically here I've got a fraction, which is 1/4, and the IB would expect that you could do that kind of math, that 1/4 is 0.25. So that's our resultant concentration, not of the 2 solutions, but simply of sodium ions, if we're just focusing in on that particular ion. Okay, here we go. We got a couple more questions to deal with. Now we're dealing with parts per million. Good times. Okay, so the thing to remember about parts per million, which makes it much easier in my opinion, is to realize that parts per million is also can be called milligrams per dm cubed. So when you get a 5.5 parts per million, that means 5.5 milligrams in 1 dm cubed of solution. And so once you have that, then should be pretty easy to convert to grams per dm cubed. You just have to move the decimal place 3 spots. Grams are bigger, so you end up with fewer grams than you had milligrams. So this is the gram per dm cubed concentration. And then the next step is to convert it to moles per dm cubed, where you recognize that you're still not changing that dm cubed unit, you're only changing the grams. And if we want to get moles, N equals mass divided by molar mass. So the mass I have here is from the concentration, and the molar mass comes from oxygen. In this example, though, it probably should be more clearly written. We're talking about oxygen, dissolved oxygen. We're talking about O2. O2 aqueous. This is the type of oxygen that fish and other marine life breathes in through their gills. And so we've got O2. That's going to have a molar mass of 32 grams per mole, and so we end up with a mole amount of 0.000172. Clearly that's not a paper 1 type of calculation, that's a calculator calculation. That's our moles, and so that's also our moles per dm cubed, because we were looking at the grams in a dm cubed, so now we have the moles in a dm cubed. Okay, the last question is a bit different. It's kind of not connected to part B. It's probably better to use the concentration that we figured out in part A. If you've got 0.0055 grams in 1 liter, and now it wants to know how much mass is there in a certain number of meters cubed. So first you've got to convert into meters cubed, and the IB will expect that you know there's 1,000 dm cubed per 1 meter cubed. So first of all, in 1 meter cubed, there's 1,000 times this much. So there'd be 5.5 grams in 1 meter cubed. And then that's just per 1 meter cubed. And now they gave us an amount of 50,000, 10 to the 4 meters cubed. So in the end, we're actually multiplying our number by 500,000, and we end up getting 275,000 as the answer. That's the number of grams, which is 275 kilograms. So even though the concentration of water is tiny, or of oxygen in the water is tiny, when we look at a big body of water that has a lot of cubic meters of water, there's actually quite a large mass of oxygen in there. Keep going along these same lines. The grams of quinine present in 1,000 dm cubed of the tonic. Well, they've told you that you have 83 milligrams per dm cubed, right, per 1. And so just multiply it by how many you have. They said in 1,000, so times 1,000. You should be able to try to set up your units and cancel out the volumes. And so times 1,000, I get 83,000 milligrams, which is 83 grams. So that's how many grams are in that amount of tonic water. Okay, going the other way, concentration of carbon dioxide in the atmosphere is currently around 9.36 times 10 to the minus 3 moles per dm cubed. So what is that in parts per million, which is a much more common way to express concentrations in the atmosphere, which are relatively low because gas particles are quite spread out. So take that 9.36, that's moles. We've got to turn it into grams, and then we're going to turn that into milligrams, and we'll have gone to milligrams per liter, and that's parts per million. So if we do moles times molar mass, then we get, I'm sorry, this is 10 to the minus 3 times molar mass. So the molar mass of CO2 is 44.01 grams per mole. I should get 0.412 as the amount of grams that is. Remember, this is the grams in a liter in a dm cubed. And then I make that milligrams, so 412 milligrams in a liter. So that means the parts per million concentration of carbon dioxide in our atmosphere is 412 parts out of every million, 412. Okay, and the final question, it says the volume of Earth's atmosphere is 5.1 times 10 to the 26 cubic meters. That's a big volume. Let's figure out how many kilograms of carbon dioxide there are approximately in the atmosphere. Obviously, this is a bit rough and around the edges, but we can still try. We've got this many grams in a dm cubed. I've got 1,000 dm cubed in 1 meter cubed, so I've converted my volume unit to meters cubed. and then I multiply it by the given volume that they want of meters cubed. So I'll get rid of meters cubed and I'll get an answer in grams. The answer is 2.10 times 10 to the 28 grams, which is 2.10 times 10 to the 25 kilograms of CO2 roughly in the atmosphere.